Okay, and now we will start talking about specific algorithms for different problems. The first problem that I'm going to talk in this video is about feature extraction and matching, which is a fundamental problem, as you know. Uh, I'm going to talk about two different relatively new solutions. Uh, there is a huge literature behind. I have selected these algorithms based on my experience, and I think they are somewhat different from the things in the past, and they are doing relatively giving a good performance. Now, the first one is SuperPoint. In fact, it's a continuation of an algorithm called Magic Point, and it is also there is an extension to it as called Super Glue, which is including the matching improvements in the matching part. First of all, the most interesting thing I believe about this algorithm, it's a self-supervised algorithm. Therefore, we are not having images, a set of images where some interest points are marked, and then you basically try to train your system. It's not like that. Okay, completely from the data, you were able to obtain your training set, and you don't have to label anything. Also, another thing is it's a the base architecture is a VGG style, a well-known CNN-based architecture. It's a VGA style architecture, and we are trying to capture the semantics, or let's call it maybe we are trying to capture the invariance with respect to different views or different lightning through this VGG style architecture. And what we have is basically using some decoders to upsample. Therefore, we first, like an hourglass network, as you can see, we are just first of all making an encoding process here so that we have a more generalization of the features, and we can have the same feature value or vector even you are looking from different directions or different rotations. Uh, we have an interest point decoder side and a descriptor decoder. Therefore, I am talking about a decoding, which means increasing back, so that at every pixel on the image with the same size W and H, I will be able to obtain some scalar value showing the probability of that point being an interest point or not. Okay? The second part is a d-dimensional of the features. Wherever you have a feature here, those vectors will be our descriptors. Okay? Therefore, we are having a detection, and for the detected points, we are having descriptions so that we can make once we after the training, once we make inference given a typical image, we will have from the image we will obtain both this part, and based on the values of the detection, we will look to the descriptions, and if you would like to find a match, we will use these descriptors to make matches on the next image. Here in this point, we are just thinking about extraction, no matching here. This is just simply obtaining the key points, repeatable key points, and their descriptions only. The decoders are here. We are having some general typical decoders. Okay, we are making an interpolation here about going to the higher resolutions. Okay, now the interesting part is the self-supervision part, how we are able to obtain key points of something without using any labeled data. The trick is threefold, like three stages. The first is interest point pre-training synthetic on synthetic images where you generate, where you know all the corners of everything. Okay, therefore it could be projections of 3D cubes or whatever, but you know their points very well. and you basically train your system so that here in this detector part, those points, in other words, this point, this point, this point, this point, will give you high values, whereas all the others give small values. This is from synthetic images you obtain after training a base detector. That's the first step. Uh, Obviously, you have to write a computer graphics code or whatever so that you have some synthetic triangles or rectangles, whatever. But at the end, those things are not labeling. These are nothing but software codes. Then I will start with an unlabeled image in the second stage. Okay, this is the first stage. In the second stage, I'm going to start with the unlabeled image. I have a base detector in my hand. I'm going to use this base detector to make something called homographic adaptation. I'm going to explain shortly. And then I'm going to have their corresponding pseudo ground truth interest points. Now, what is this homographic adaptation? Let's look at that part. These are all synthetic, okay? Now, this homographic adaptation is this. You have an image and you have a base detector, okay? Then what you're gonna do is you will have some random homographies of this image. You will just do whatever you like, okay? And after this warping images, you have warped images of the same scene, okay? You have warped images of the same scene. Then you will apply the detector, okay? Then after this detector, there will be some responses, okay? Starting from here, you will have some responses. And those responses, for example, this response is an character A, which is a normal orientation. You have some responses due to the space detector. You say that you have to be here, you have to be some key points which are important. Now, the interesting part, you rotate your homography here, you rotate it, then apply the detector. The detector will create some at other points of a rotated A. Now what you're going to do is you will just undo your homography. You will undo it and you will obtain back some other points. And if you continue like this, there will be an aggregated heat map. In other words, you are memorizing in a way for a typical image. If you have corners at this orientation, once you rotate it, your system will create some other ones. And those points, once you rotate it back, you will obtain your corresponding points at these aggregated heat map. Therefore, with this way, I obtain nothing but a number of interest points, a number of interest points which are including different orientations of the objects as well. Okay? Now, I'm going to do a final joint training here as a third step. Okay, as a third step, I'm going to have original image, a random, completely random warping. Okay, and then I'm going to have the SuperPoint, my new SuperPoint, where I'm going to train them saying that those aggregated points here and here, whether it's random, you are enforcing the system. You have to have with these aggregated points, you have to try to obtain interest points. You have to maximize this map here by using increasing those points, because I have already memorized for this particular image where should be the corresponding homography adapted rotated key points are. And with this kind of a scenario, I'm gonna have those points. I'm gonna train my super point network in such a way that I would like my system not only for a limited number of interest points, but all the others aggregated super points to increase. And then, since I have a control of everything, I know this warping, I can match everything to everything. And what I'm going to have is also, I would like to have a descriptor loss saying that the corresponding features, the corresponding feature behind this and behind this, just the center of this train, their descriptor vectors should also be similar. Okay, therefore you are saying that SuperPoint algorithm, this network, you are saying that you have to be trained in such a way that you have to be capable of generating the aggregated interest points superset, plus during those rotations, you have to be able to have this points descriptor and that points descriptor, or this points descriptor and maybe not that one, but maybe this point descriptor and this point descriptor. They should be also similar. You will enforce this thing together. Therefore, we are looking to the detection side. We are looking to the description side by looking to those homography points on the a set of self-labeled interest points. Nothing labeled manually, everything is automatically obtained. What are the typical results? These are random homographic warping, okay? But we know they are warpings. Still training is going on. Then what I'm gonna do is I know which point matches to which point, okay? Hopefully, not necessarily all of them will be matched. Don't forget it, because this random warp is not trained by yourself. Maybe it cannot create all those points, but still, there will be a few matches. And if you are saying that their descriptors should be similar to each other, and we will have a cross entropy loss for the detector. Okay, here cross entropy loss saying that you have to be maximum at those points. Okay, now as you can see, there are two images here, a wall, and the wall is perspectively observed from a different direction. Another one, there is a house here, and this house is also looking for a different perspective. And finally, the same scene, day and night. That's interesting. Day and night, and they are again, as you can see, or if you can check it, you can see that the corners are very, with good precision, are able to be matched. Okay, this is a CVPR 2018 paper called SuperPoint, which has an interesting idea of complete self-supervision and utilization of some homographies to aggregate some key points at different views and trying to match the descriptions of these points with random warpings. Okay, this is the SuperPoint algorithm. I'm going to talk about another one. This is a D2net, again, relatively newer one, CVPR 2019. Okay, that's also an interesting concept. This time, the authors are trying to do something together. All the algorithms available about feature extraction and matching, there is always first detection, and at the detected points, we have a description. Now, the authors are trying to go to a feature space, and in that feature space, they are trying to obtain, using the same feature information, both the detected point and its description together. Okay, therefore there is a dual role at the end of the network, at the feature space of the network. Now, how I'm gonna do it? This is supervised. I need some data, okay? And I'm using, that's also interesting, again, a VGG16. I'm gonna use simply nothing but I'm gonna start from a VGG16 network off the shelf, and I'm gonna try to uh, train on top of this VGG network with my some extra costs. Okay, now there is a concept of triplet margin, which is in metric learning literature. Just for simplicity, I'm gonna say if you have a reference and if you have a positive sample and if you have a negative sample, what you are trying to do is you are trying to go to a feature space where Reference and uh, positive will be more nearby. In the meantime, the negative will be go far away. This is the whole aim. Your cost is determined in such a way that you are trying to make positive things. When we say positive, here, if you have a point on one image and on the other image, which we know that they are matching on the same point in the scene, they are positive pairs. If there is another key point not belong to the same points, they are negative points. We would like to go to a feature space where matches are coming nearby invariance, and in the meantime, all the other matches go far away. But this is about certainly about description. How do you detect those points? Now, that's the interesting point. A typical network, as I have said, first try to find the points, and for those points, it makes descriptions. Okay? These are the pink ones are your detections, the blue ones are your descriptions, and this is called detect, then describe. This is the conventional technique. We know from SIFT or SURF, many algorithms are like that. This paper says together D and D, that's why D2 is coming from. This D and D gives you at the very same tensor, you will say that this tensor vector is based on the values over inside the vector. It's a detected point, and the whole vector is description. Just a single data doing those things together. Now, this triplet margin is about description. Positives, matches should be similar, unmatches should be far away using labeled supervised data. The soft detection is this. In SIFT, we know that. In SIFT, we know that x, y, and the scale, there is again a vector, and we are trying to maximize with respect to all your neighbors and with respect to all the scales that you have. Now, this paper aims or hypothesizes this idea, okay? Let's say we have a tensor that we obtain through learning process using some CNNs, whatever, a VGG, and you obtain at any point a local descriptor. This is your vector, okay? Now, what I'm gonna do is, if I have my points which are larger with respect to my local neighbors, which are larger with respect to my local neighbors, X, Y, Z, or in a special space, then that will be a possible maxima, local maxima. Plus, if your ratio, if your ratio to the maximum value is again something large, we understand that you have also a strong indication in this feature space. Okay, therefore, these are features. Okay, these are features. And for that particular feature, we have a strong information. Okay, therefore, this non-local maxima, okay, and this ratio to max, okay, those information are multiplied and we try to find a maximum of it in different detections here. Therefore, what I'm trying to do is I'm trying to find something which is larger than our special neighbors, and in the meantime, we are larger with respect to my neighbors. We simply multiply alpha and beta. The authors do it like this, and we try to maximize in this direction. Okay? And if you find such a point, that point will be your soft decision score. In this point, you will say, I'm going to have nothing but important information, which means at one particular point of the feature with some particular XY position, there is a maxima, just like in SIFT, okay? Therefore, this is the way you will fill your soft detection module. And in the meantime, all the vector, the remaining vector here will be your descriptor as well. Therefore, The detection and description are achieved together, where the descriptor is the vector that you are learning through a process supervised. And in the meantime, your detection scores are obtained through the soft detection scores. Okay. Now, this is obtained by positive and the negative samples in metric learning concept. Once you have matching, you can do it. And in the meantime, the detection score that we are using for detecting is combines the local and the channel-wise maximum. Okay, therefore, in the feature channel, you find the maximum, and the local information you also try to be maximum. If you have it, you have a high number, and you put those points here and here. Now, by this kind of a training, the network tries to from supervised data, which means you have some points which are already matched. They find some points, not only maximizing its soft detection module for detection, in the meantime, matching points on different images as positive examples. They try to come nearby using a soft triplet margin ranking loss. In the meantime, all the other points are trying to be negative samples. You try to make them far away. There is a combined cost, this one together with this one, and this cost is minimized. And what you obtain is this remarkable result. Okay, this is an image versus a drawing, the image versus a night time, and there is a window, and the system is just basically matching the outside buildings through this window. These are real good performances with respect to all the SIFT, SURF, whatever. And right now, there are many other algorithms also trying to beat these techniques. Okay, that's all for feature extraction and matching. Two algorithms. That's it.